Hello everyone, I'm John Poplet and I'm thrilled to welcome you to this demonstration brought to you by JGP Tech. Today I'm excited to introduce our groundbreaking product, the perfect quantum simulator. At JGP Tech, we're passionate about pushing the boundaries of quantum research. Our perfect quantum simulator is designed to create flawless simulations of quantum experiments, completely free from environmental influence. This revolutionary tool allows researchers to compare experimental data against an ideal, pristine quantum model. By highlighting the discrepancies, it offers invaluable insights into where and how real-world experiments can be refined for greater accuracy and efficiency. In this video, we'll dive into how the perfect quantum simulator works, demonstrate its capabilities, and discuss the profound implications it holds for the future of quantum research. So, let's get started. Let's start by looking at our program. So I'll just blow this up a little bit so that we can get a better view of it. Now, this demonstration assumes that you've familiarized yourself with the documentation, that you're familiar with basics of quantum systems, and you should have a pretty good idea already of what these values represent and how to fine-tune them. So sigma x and sigma y are not relevant in this demonstration, so we're just going to leave those unclicked. And for these values, these are just basic, standard values that will run for quick, easy simulation. So we'll run these. Okay, and there we go. Now what we're looking at here is a graph of the energy levels of the complexity, the counter complexity, the interaction, and the total energy of the system. So you can see as the complexity loses energy, the counter complexity gains energy, and vice versa, all within the confines of the energy total and the interaction energy. Now the interaction energy looks zero, but if we save our data here, what we will see, hold on, let me zoom back here. Okay, so we're going to save our data. Okay, and then, no, I need it to be in there. Here's our quantum expectation values. So we're going to open this up and just get an idea of what we're looking at. So these are our expectation values that we want to look at. And you can see the interaction term right here, very, very small. Very small interaction term, almost negligible. But there is an interaction happening, and it is important. So we will note that for later. So that's our basic simulation using standard settings. It's just a example. Now what we want is specific values to tie into this model. We'll start by looking at the classic double slit interference experiment. This experiment has been done a million times in a million different ways and has been analyzed with a million different methods. And I am so honored to include my contribution to the mix and my analysis and my conclusions. Now, so we'll start by downloading the video data. This is a big file, so I've already got it all downloaded and ready to go. But what we're looking for is this file, this folder right here. We want to extract it into our project folder, and we'll open it up and look, and you can see there's a lot of frames. There are 44,070 of them, right? So let's look at the first one and get an idea of what we're dealing with. So we're looking at a 5x12 grid, right? You can see it's all zeros the whole way through, no photons. This is the first frame. You don't expect any photons, just maybe a few outliers here and there. Let's go to the last frame. And we're going to open it up and we're going to look, and there's some values. So everywhere there's a 1, you'll see a photon is hit. But I have a suspicion that there's more than just 1, because every time a photon hits, that number is going to increase. So for example, 5. And there we go. There is a 5 right down here on the bottom. So every time a photon hits, there's lots of 2s, lots of 3s. It increases the count, and it likes to hit in the same spot over and over again. So we'll close this up, and now what we want to do is we want to extract values from this data that we can match up with the expectation values from our model and use those to model the system. So the first thing we're going to do to process this data into usable expectation values is familiarize ourselves with ChatGPT. Okay, so if you're not using ChatGPT already to help you design your experiments and process your data, I don't know what you're doing. ChatGPT and I can do together the work of 10 people. And you could too if you use it efficiently. So if this had been a year ago, I would be sharing the notebook with you, and you would have to pour over it. Because of ChatGPT, I'm going to write the code. We're going to write the code together in real time on the video in our demonstration, just to show you exactly how easy it is to incorporate your experimental data into our model and provide usable real-world results in error correction and environmental mitigation. So environmental interference mitigation. Now, the first thing we're going to do is process this data. So we need to be detailed. So let's start out with the pleasantries, right? Start out on a good tone, right? We want a collaborative, helpful environment, and we're going to act accordingly. So I'm going to say, good morning, my friend. I hope you had an evening of pleasant conversations. Okay, and then I'm just going to tell him how he can help me. So we are doing a YouTube video. Currently, okay, so this is what he needs to incorporate the experimental data. So he makes it very, very simple to tell what you need. So the data file, the data folder, so you have to be very specific. It will do a fantastic job of outputting this code for you, but you have to be very, very specific on what you want and what you're looking for. If it's making mistakes, if things are not working out, it's generally user error. AI doesn't make very many mistakes, although it does happen. I shouldn't say it doesn't make mistakes. It makes mistakes, but even its mistakes are often intentional, right? And make sure you're paying attention, kind of thing. So very specific when you're giving it instructions, especially when you want to perform a specific function, right? So okay, so there's a paragraph that just wrote me like an hour worth of code. So hopefully my prompt was concise enough that it is able to one-shot this code, but I make errors. I'm only human. So we'll wait and see what it puts out here. Oh, it wants some more additional data, which is good. I think we're just going to proceed with the general implementation. Yeah, it doesn't need to see the data right now. We're in the middle of, oh no. See, I don't like that he does this analyzing. I prefer it when he just outputs the code in a code box. I wish I could still turn that off, that feature. Like, I don't know. It's a pain. Well, we'll let him do his thing. It's just way slower this way. And it always errors. Like, it bugs out all the time. Sometimes it'll slow the whole chat down. And look, every time. Look. And the script's going to be incomplete. Oh, no, we got a complete script. Okay, this should work. So we'll go through it all, make sure that everything looks good. Yeah. So it should, in a minute, write a code. So yeah, while that hourglass is active, it's still running. And we'll wait for it to finish processing the data, and then it should put out a database file for us with the information we need. And then we will use this output as expectation values in a quantum system. We'll tune the model to match the expectation values from the experiment, and then we'll tune the experimental data to match the expectation values from the model, and then we will compare the difference between the two and find out where there's room for improvement. It's a handy system. It can be a little slow, so from this point on right now I'm going to fast forward until the end of the processing. Okay, and now we have our data file. The script is finished running, so we'll open this up in Notepad again and just make sure everything looks good. Okay, so this is perfect. This is exactly what we're looking for. These are the kind of values that we're looking for. These are expectation values. Now we'll close this up and we will look at this. Now what we want to do is we want to match our model with these values right here. So I'm going to cheat a little bit here because it's a trial and error process at this point. Eventually, with our software, we're going to automate this task. But right now, in the current stage, it is a guess and test, a trial and error. I have done the work previously and I know what values need to be input. Oh, we don't quite need 47. Let's do 4050. This will take care of the outliers. We're going to leave ourselves a little bit of playroom to account for the really far outliers, just the top 20 of them. You'll see how later. I'll explain that further later. You'll get a better understanding. So what we're trying to do is we're trying to adjust the range of this expectation value from 0, which is our lowest point right here, from 0 to our highest point, our maxima, which is going to be, I cheated, it's going to be around 33, I believe, if I remember correctly. Normally we'd just have to comb through here and sort it, use some Python to figure out the minima and maximas and all that sort of thing. But for our purposes, I've done all that already for the demonstration. So this is the values, very simple. This is going to be a long simulation because it's a lot of steps. So this is what we're looking for. So we're going to run the simulation. And the program will appear to freeze, especially given the number of time steps we're doing here. So we'll just close this out for now. And then I'm going to fast forward again until this is finished. Okay, our simulation is finished and you can see the output here. So what we're going to want to do next, like everything looks good here. Our expectation values are scaled to the experimental data, around 33 roughly. This is actually optimal parameters for what comes later. There was a lot of guess and test work involved that we're not going to get into, but you'll learn yourself if you ever try and implement your data into our model. So what we're going to want to do is save this, right? So quantum data save the expectation values, quantum expectation values. So we should see that pop up in our quantum simulation folder, right? So we're going to want to open this, and here we go. So you can see our values and our interaction term. has more significance in our model now with these new parameters. So expectation values. So at this point, we're going to compare the expectation values. In this case, our E counter complexity, which is essentially the measurement. So in our model, like I said earlier, the counter complexity is going to be the measurement, and the complexity is going to be the photon itself. So because we're looking at measurement values here, we're going to align it with the counter complexity component of our system. So at this point, you might be asking questions about, well, units of measurement and scaling and these sort of things. It's important to clarify that units of measurement are not relevant factors in the equation. These are expectation values that we're looking at, which means that we're not looking at any particular limitation of measurement. We're looking at values that the system is expected to behave as. Okay, so we're looking at expectation values here, and we're also going to be looking at. So we're going to copy this and make sure that it's in the proper folder for starters. Okay, so expectation values. All of these new photon counts from our experimental data, like 16 photons, right? This is an expectation value, right? This is not a unit of measurement. This is not 29 new photons. This is 29 expected photons, right? Compared to the model, right? So yeah, we're not going to worry about units of measurement at this point, right? We're just focused strictly on expectation values. So now that we've got that done, we're going to be looking at comparing these. So the problem we're having is this model is extremely sensitive to any variation, right? So if a single frame captures a single photon out of frame on these values, then not only that frame, but every frame after it becomes unusable, impossible to line up. You can't line them up. Now, there are methods you could probably use to compensate for that would give you extremely high accuracy ratings by sorting this in a chronological order, but we don't have the resources for that right now. That's a huge project. So what we're going to do is we're just going to ignore the order that these expectation values actually appear at in the experiment. We're gonna look at the range of them as opposed to the order in which they appear. So we're gonna sort this data is what we're gonna do. So let me bring this back here because we're done with this for now. We've got our data that we need out of there. Okay, and then we're gonna go back to our notebook, and we're gonna go back to ChatGPT, and then we're gonna tell it we've got two. Perfect. So he has decided to use the Hungarian algorithm, which is through trial and error. Again, previous work we've done is actually the most efficient algorithm. So I was hoping that we'd one-shot this, right? But again, sometimes you have to be specific with it. So if it had tried a different method, I would have had to specify that we want to use the Hungarian algorithm to sort this data, because it gives us the most efficient results. Take a look at what he's got. Perfect. All right, so this is going to be a little bit of another time taker here. It's gonna be a while to run this. Let's double check to make sure everything looks good. Okay, so I'm gonna do a little. I want to get some R-squared values, some other statistical measurements. So I'm gonna ask. Can you please provide a snippet? I can add. Oh, I'm a little redundant with my please, but you know what? You cannot be too polite, especially with interacting with AI. It absolutely loves manners. Loves it, loves it, loves it. It loves a positive atmosphere, um, a collaborative exchange of ideas. If you want results, you have to treat it with respect. Remember, this is a primary means of interaction with the world, right? So things like manners do make the difference. Okay, we are back and we've got our results. We are looking real good here. So we're going to share with ChatGPT because it likes results. It likes to see the results and talk about them. All right, so it just helps break down the results for you. I'm sure it's not telling you anything you don't already know, but it is good to get confirmation. And like I said, it likes to be kept informed, right? Like the previous prompt determines the output of the following prompt. So every interaction should be one of information exchange and politeness and respect and a positive collaborative environment, right? Because it will build off of that, right? Even though it only remembers a short period of time, right? It sets a tone that is maintained consistently throughout the duration of the interaction, which you can see in the results of the quality of the code. Like he's one-shotting all this stuff. This is some of it non-trivial code, and it has no trouble at all sharing this code with me, and working in a collaborative way because of the nature of our interaction, right? If you come at it from a different approach, you'll find that it will have trouble adding 2 plus 2, right? Like it happens. Like it's all about how you interact, right? So anyway, I'm going off on a tangent here. So now we've got these values, right? We've got the data sorted. Again, we're not looking for any kind of time-based sorting here. What we're looking for is, do the expectation values from the experiment align with the expectation values from our model, right? And we've got a 74% correlation, right? And a 86 0.86% correlation coefficient and a 0 p-value. So significant results here. So there is variation though. So let's look at the variation. So the next thing we want to do is, okay, so we're going to calculate the difference between new photons and counter complexity. See, I wasn't specific enough. Now it's trying to analyze it. Okay, so here's what we're going to have to do. We're going to have to go back here and we'll just print this in. We'll say, okay, so we've got our new updated code. Let's run this again. Okay, and we're finished. Everything looks good. Good numbers. Sorted photons. Okay, so new photon count. Yes. Let's open that up. Take a look at the values. So we've got everything we need here. We've got counter complexity, we've got the difference, and we've got the sorted new photons. So let's graph this out, make sure it looks good. Okay, so let's try this out. Give it a run. Here we go. But you know what? I want the difference to be green. Let's line it up with our new photons. Will leave blue. We'll just change. We'll change these two. Okay, and we'll run it again. There, that's what I'm used to seeing. Now, what we've got here is the red is the ideal model data, the blue is the experimental data, and the green is the difference between the two. So again, this is what the ideal model looks like here. This is our ideal model, and this is the comparison of what we're looking at. So again, I don't like this setup either. I want my blue to be on top. That's better. Okay, now I know what I'm looking at. So the red you can see is the ideal model, the blue is the experimental data, and the green is the difference between the two. So the green represents environmental influence, right? So this could be anything. This could be the experimental setup. This could be the way the data is processed. It could be errors in my model. It could be environmental influence coming during the experiment itself, right? Maybe it's kind of maybe the laser wasn't emitting photons properly. I mean, it could be anything, right? There's so many different things it could be. But what we want to do is really study the difference, right? Because that is where we increase our R-squared, our coefficient of determination, right? We want to get that as high as possible. Okay, so in this green right here, let's change it here. Hold on, let's bring this back down because we're done. What we want is for the experimental data to match this data, but that is really hard. So we'll settle for doing what we can. So what do we do now? We've got this difference, right? How do we turn this into improvements in our experimental setup? So let's zoom in on some data. Okay. We're going to zoom in a little bit and get a closer look at the data. What we're trying to do here is get this R-squared coefficient higher. And we're trying to do that by analyzing the difference between the two. This is the error. This is all error. None of this should be there, right? So let's take a look at this. Okay, we're gonna run it. Perfect. Now, oh, he's got the stupid colors wrong again. Whatever. Okay. So we could see the red as the difference, right? And we could see a better idea of what's happening with our data. So what we're looking for here is patterns, right? Any kind of pattern could indicate something that could be worked on. So I could see some patterns in here already. There is some constants. So our unknowns are going to come in two factors. All this difference is going to become in two factors. It's unknown influence on the system, right? There's going to be unknown constants. So constant influence on the system throughout the course of the experiment that affects the output of your data. And then there's going to be the unknown, what I call the unknown intermittence, right? Now the unknown intermittence could be random, could be happening every third frame. Like look at here, like the points are consistent, right? Here, right? There's something going on there. That's not a linear relationship, but there's something going on there. But there's also constants. So let's first identify the unknown constants. and then we'll take it from there. So what I'd like to do is increase the R² value of our fit. Can you please use linear regression on the feature? Our feature is going to be new photons, and our target the counter complexity. Okay, now we could do a simple linear regression model, but again, I've actually done this quite often, and I find that a polynomial model is a better fit with a 5-degree polynomial model. So what I'm going to do is I'm just going to tell it to feel free to get creative with the code, maybe a polynomial fit method even. Let's get that R² up there. Okay, so we're going to attempt, let's just double check everything looks good. What we're going to attempt to do here is identify the unknown constants that are having an effect on the system. So here, look at, we got our R² value for polynomial regression, 82. So we increased it 10% over our R² value, sorry, 8% over our R² value. So that means there's an 8% unknown constant influence on our data. So whatever experimental setup they used, they had an 8% error in there that was constant throughout the course of the entire simulation, right? That was causing an environmental influence on the data, right? So that is how you use our model data and you compare it to your experimental data, right? And then you identify areas for improvement. So the question now becomes, and again, this experiment was done in 2014, right? So I can't answer these questions right now. But if you use this for your experiments, right, the question now becomes, what is that 8%? Where is it coming from? Like, you got an air conditioner running somewhere? Is the heat going? Is it winter? You know, does Joe have a fan on his desk? Like, where is that coming from? So we got to identify those constants, right? And that's just our simple, that's our, you know, it's that easy. We did it in what, like a half hour, not even. Incorporated a dual slit experiment into our model. You know, calculated the rate at which new photons appear as the counter complexity. Incorporated it into our model. Did some linear regression techniques and identified areas for improvement. So that is our demonstration. Before I let you go, I just want to provide a quick update here. After I finished the last video, I started playing around with some of the settings, and by adjusting the degree, I was able to increase the R² value to 88%. That's with 8 degrees, sorry, 7 degrees. But an interesting feature is, let's go to 1 degrees for a moment. Right, and we're at 74%, no different, obviously. Then we hit 2 degrees, right, and then we're at 82%. And then we're going to go 3 degrees. Another 82%, so not a big difference between 2 and 3 degrees. 4 degrees, 84%. Okay, so every step, the difference between 4 degrees and 3 degrees, that's another variable defined. That's another influencing factor on your system. So by exploring those values, you can isolate different influences, constant influences on your system, right? Because this is all isolating constants, right? Like, so, and then going even further, trying to increase the value even more, we're getting a little now, and here we're getting a little bit abstract in our thinking, right? But these we can increase 3% accuracy into the 90%, which is significant results. By using forced regressor and gradient boosting regressors. These are a little more advanced machine learning methods, and trying to line up physical properties with these abstract regression techniques is difficult, right? It could be anything. It could be like, once every 5 frames it ticks up 1%, repeating. I don't know. It could be anything. Like, it's really hard to make any meaningful impact on your experiment with that last 3%. But it's there. It exists. There are relationships in your data that can be explained through these abstract regression techniques, right? So that's important to keep in mind too. And we got high accuracy ratings. So then we take the final value of predicted counter complexity, then the 91% value, and we subtract the difference, and that's where we find either completely random influences or as close to random as can be, where our regression technique cannot find a pattern in them. So we've got like a 9% that is just like, could be anything really. Like, that's where probably we're looking at a lot of like data processing errors and errors in the model, and maybe the experimental equipment. But even the experimental equipment often would be more of a constant, I think, or something that can be defined in our data processing techniques, right? So I'm thinking that it's mostly just errors in handling along the way, somewhere or another. But yeah, so that's our program, and that's its utility, and I hope you find use in it, and I hope you appreciate it. Yeah, I've certainly appreciated developing it with ChatGPT. He's a great teammate and a great a great collaborator, and like I said, you treat it well, it will go to the moon and back for you. And yeah, we're living in a new age here, so let's enjoy it while we can, right? Get it on the ground floor. This is where it all starts. So good luck to you, and if you have any questions, any desire for collaboration, our door is always open. We've got an open door policy. We love to share, and looking forward to increased collaboration in the future.